moving to the next talk, which we're going to be pleased to hear about, Eran Assaf is going to tell us about definite orthogonal modular forms, computations, excursions, and discoveries. The floor is yours.
Thank you. First of all, I'd like to thank the organizers for accepting the paper and letting me speak here. Also, like Alina, it's my first time in Bristol and my first time in person in ANTS. I really enjoy it. It's a very colorful city, and I think it's a wonderful conference. Happy to be here. And at first, I thought, okay, this would be a good time to tell you about automorphic forms and Langland's functoriality and endoscopy. And some people can pull it off, like Catherine did before me, like got really complicated stuff. But it's Thursday, and I'm the one thing keeping you from your lunch. So I thought, maybe not. So instead, we're just going to have some fun. So we're going to have just fun with L functions. Just bear with me. I won't explain much. I'll just show you some things. Luckily, you all know what a lattice is. And now we just perform some magic. We have this complicated machine. We feed it lattices, and it spits out L functions. Sounds like a great thing, right? You just have this machine producing L functions. And it produces, I mean, it's fair to say that it doesn't produce L functions directly. It produces this object called orthogonal modular forms, which we will get back to later. But right now, we don't have to know what it is. It's just some object that has L functions related to it. So here's an example. So I'm taking a small lattice, rank 4, discriminant 37 squared. And this is its Gram matrix, very nice looking lattice. We just feed it into the machine. And we get, for example, for one such orthogonal modular form, we get just a product of zeta functions. Not very interesting, you might say. We all know zeta functions. Nothing very interesting is happening here. But then we have another orthogonal modular form, and we compute the L function. And now I switch notation. Before we had L function depending on S. And now I'll just look at the local factor at P, and I look at it as a polynomial in P to the minus S, because it will be more convenient. So the first product of zeta functions just turned into the product of these polynomials. And the second one suddenly has the appearance of a modular form, which is really nice. And I would like to thank Juanita for the idea to allow non-Zoom participants to also be able to click on the link. I hope it's big enough. But you can take a look at the LMFDB page and see what the modular form is. Similarly, we get another L function corresponding to a modular form with a different modular form, again, of level 37 and weight 2, and trivial character. Not a coincidence. Well, this is very well known. And those of you who has, oh, before that, sorry, there's another one. There's a fourth orthogonal modular form. This one is slightly more complicated. It still corresponds to the same modular form that we've seen before, but in a slightly more complicated way. Oh, that's a shame. How do we move this part? Okay, I'll just tell you what's written there. So this is ANTS, and we're interested in algorithms and timings. So you can read all the fancy tables in our paper, but just for now, the computation of all these L polynomials for P up to 100, it's just like 2 minutes computation on your laptop. That's nothing too difficult. Okay, now those of you who might have noticed, these L polynomials had a certain shape corresponding to actually the symmetric power of the L function. And here, this is something called the Saito-Kurokawa leaf. You don't need to know what that is. You can think of it as just the tensor product corresponding to some Eisenstein series and our form F. So we have all these L functions coming from modular forms. Okay, but you say we know modular forms. So you got some L polynomials coming from modular forms. What's the big deal? Why is it interesting? And again, you can time it. So this time, I only looked at the timing for P less than 20, just like 2 seconds. If you go up to 100, it really takes 2 minutes. The reason I'm only looking at p up to 20 is because later on, running times will be longer and going up to 100 might be difficult. Okay, so we can go to higher rank. We can go to rank 6. So in this case, we have a lattice of rank 6 and discriminant 39. And we find two orthogonal modular forms. The first has a polynomial that looks like, again, zeta functions. And the second one, slightly more interesting. Here we find not the symmetric square of a modular form, but rather it's twisted by a character. That relates to the fact that the discriminant here is not a square.
Just clarify one thing. So when you give these timings, that's the time to go through the orthogonal modular form.
That's the time to compute all these L polynomials that you've seen there for P.
Why are the orthogonal modular forms? I mean, if you use the right-hand side, right? If you already know this identity.
That's from the lattice to compute the L polynomials. Total time for everything. In the paper, you can find more specific timing, like for every P and things like that, and how much time it took to compute the space of orthogonal modular form and to diagonalize it, things like that. Okay. So yeah, that character there, that's that was something I had some issues with. People tell me I have some character issues sometimes. It was difficult. But here you see already in rank 6, even for primes up to 20, it takes more than an hour to get those L polynomials. And you can imagine that it only gets worse. So here's an example when the rank is 8, discriminant is 53. Again, we have some orthogonal modular form. There are many. I'm just focusing at one because it has some new phenomena that we've not seen before, and you might have expected it because we're going up the ranks. Here we have some irreducible factor of degree 4 that does not seem to relate to any classical modular form. Okay. What do we do with it? Well, first of all, I'll tell you that this already takes much longer, even from primes up to 10. And the reasons will become obvious very soon when I talk about the algorithm. Yes, but what is this polynomial of degree 4 and where does it come from? What is the automorphic object it corresponds to? So these are questions that we were asking ourselves. Another question is, how do we prove all the identities that we had before, right? We see them for P up to 100 or up to whatever we can compute, but we want to say that they're true in general, right? We could try to fit it to Lin, but I don't think we're there yet. Yeah, and as I said, I want to know where does this polynomial come from. So now I'll have to look under the hood a little bit and tell you about the magic that we're doing with the lattices. If you remember that part, tell you a little bit what orthogonal modular forms are. So it will be quite quick. If we have a lattice inside a vector space, we can look at its genus. So the genus are just all the other lattices in the vector space that are everywhere locally isometric to it. And it's a way that we have to measure the failure of local global principle for lattices. And the class set is just a set of global isometry classes inside the genus. That's the main thing we will work with. Inside this class set, we have a notion of neighboring lattices. So this is an old theory by Kneisser. This is a theory of P neighbors, or more generally, P to the K neighbors. Most of the time, I will only talk about P neighbors, but we really need P to the K neighbors to produce the L polynomials. So I'll just say P neighbors, and you'll see whatever's on the slides. So it gives an effective method to compute the class set, but also it gives some nice operators on this space, on this class set, which is actually a hack action. So we start with any good prime that does not divide the discriminant of the lattice, and we can have P equals 2, and that's important because some things you can only compute for P equals 2 because of running time. So we say that an integral lattice is a P neighbor of our original lattice, and we write it like that. If the intersection has index P inside both the original lattices. So all isogeny people here, and Alex will also be talking about it later, this is the same as a P isogeny. Okay, like traversing the graph supersingular elliptic curve through P isogenies. More generally, for a billion varieties. So we notice that if we have two P neighbors, then they're everywhere locally isometric. So we get another thing in the genus. And it's quite easy to produce P neighbors and actually enumerate all of them. And moreover, we can use that method to produce the entire class set. So we can, I mean, most often we can use one prime and just go over all P neighbors until we produce all representatives of the class set. If you worry about termination, there are class formulas for lattices, and we can know when we're done. Here's an example, because so far everything has been very theoretic. And I'll go again for something small, rank 4, this time a discriminant that's not a square, 29. So here the class number is just 2. And it's very easy. We start with this lattice, and there's a non-trivial class represented by this 2 neighbor. As you see, we're just multiplying by 2 one basis element, dividing by 2 the other. Very easy. We get another lattice and form the entire class set. So what are orthogonal modular forms? These are just functions on the class set. Very easy. Complex valued functions on the class set. And we can use the P neighbor operation to define the Hecke operators. We just go over all P neighbor lattices, find out to which class they're isometric, and this is the result that we get. This also sounds very theoretic. I should say that these are all self-adjoint and they commute, and we have common basis of eigenforms. As always, that's the thing we like to do. But here's an example to make it feel concrete. So as I said, for discriminant 29 and rank 4, we have 2 lattices in the class set. So the Hecke operators are just 2 by 2 matrices. And you can see that for every Hecke operator, the sum of the numbers in each column is constant, because it's just the number of P neighbors. And we just go over them and check their isometry classes, and we get these numbers, and we can compute the eigenforms. So we get 1, which we always get the constant function, just sum over all the lattices. That's what we call an Eisenstein series. And it's pretty easy to see that the Hecke eigenvalues look like this. But we also get another eigenvector. And this one, we get some Hecke eigenvalues. And okay, you say, let's try to connect them to some classical modular form. Well, they're not connected to any. So these come from a Hilbert modular form. And again, if you want to click the link, it's right here. So this is part of what we did. We explained in rank 4 everything that could happen, all the eigensystems that can occur. The square discriminant case was already known, but we contributed for the non-square case. So let's get back to the L functions from the beginning. Right. So this is just notation. The discriminant has some sign issues, but what's really important is that there's a family of natural theta maps. One of them you probably know, just the theta series of representation numbers of the lattice. That happens if you plug in G equals 1, and you get a classical modular form. But one can push that further and obtain what is known as a Siegel modular form. So if you had a seagull waking you up at night, then I'm also constantly being bothered by Siegel. So we get Siegel modular forms of higher genre and character. And it's a consequence of an old theorem of Raleigh's, but it took us a while to figure that out. It's not spelled out immediately. That one can, in general, conclude that if we have some of these natural theta maps not vanishing, then there's a relation between the L functions of the Siegel modular form and the orthogonal modular form that we started with. And that's this nice theorem, which helps explain everything that we've seen so far. For example, if G equals 1, then you obtain here the L function corresponding to the symmetric square and some zeta factors. And if you want to obtain some relations between the Hecke eigenvalues, then you can just read off the coefficients and you obtain formulas for the Hecke eigenvalues of the orthogonal modular form. I'll remind you that these Hecke eigenvalues are simply Hecke eigenvalues of the adjacency matrix in our p-neighbor rule. Okay, what can we do with it? So here's a sample application. It's a nice theorem. Take lambda to be A6 plus A2, that's a rank 8 lattice. There are 3 eigenforms there. Their eigenvalues are given by this. The previous theorem just tells us that, where the APs and BPs come from modular forms and chi's corresponding character. You'll note this lattice has discriminant 21. But maybe another way to look at this same theorem is that there are some explicit matrices for which the adjacency matrix is just the linear sum of these Hecke eigenvalues, these orthogonal modular forms. So it's a really nice expression for these p neighboring matrices. Okay. So when G equals 1, things were really easy. We just got classical modular form. But we're interested in what happens when G is larger than that. So I'll just introduce the notion of depth, which is the smallest integer for which theta G is non-zero. Here's an example in rank 6 and discriminant 75. We take some orthogonal modular form of depth 2, and it appears that its Hecke eigenvalues satisfy this formula when we compute it for many primes p, where again f comes from some classical modular form. So it turns out that the theta 2 of this orthogonal modular form is the Saito-Kurokawa lift of f. So we have this nice relation between the L functions. So again, everything is described in terms of zeta functions and L functions of modular forms. But more general, this is a special case of something called Aikido lifts, which represent the L function as product of GL1 and GL2. But as we've learned, when we go higher, this is not always the case. And we're back to the rank 8 discriminant 53 case. So recall we had this degree 4 polynomial. And we compute and see that this is the depth 2 case. So the theta 2 of this orthogonal modular form is non-zero. So we know by the previous formula that we have this kind of relation between the L function of a Siegel modular form with character and this degree 4 polynomial. And since it is irreducible, which is a fact that we know only from our MIMA computation, and then you can ask, well, how do we know it's true? After Frederick's talk, I'm not sure, but we have some sanity checks and we hope it is, like many results that we're basing our work on. So hopefully that's fine. But that means that F is a non-lift Siegel modular form. So it doesn't come from a classical modular form. And we have this following relation between the eigenvalues. And the nice thing here is that we don't know of any other method to produce this Siegel modular form with non-trivial character. So we only know it exists because of this computation. And in the last few minutes of the talk, I would like to talk about another application of what we did, the thing called Eisenstein Conferences. So maybe one of the most famous example was given by Chenevier and Lan. So if we take the lattice E8 plus E8, there are famously just 2 lattices in the class set. This is like, can you hear the shape of a drum? Right, that's the answer for lattices is no, and this is the famous example. So we have E8 plus E8 and E16, and we can compute, again, just the matrix of the Hecke operator at 2. In this case, we can't compute like much further, but the Hecke operator at 2 is enough. The constant function is an Eisenstein series. And we have another eigenvector. with coefficients 405 and minus 286. And again, one can check that it comes from a classical modular form, specifically the discriminant. So we really get a relation between tau of p, the partition numbers, and our Hecke eigenvalues. One can see that if we multiply the first eigenvector by 286 and add it to the second one, then we get something that vanishes modulo 691, which shouldn't surprise anyone because it's the famous Ramanujan congruence. Now, I'm lying a little bit in the arrow in the end there. There's some work to do there to go actually to the Galois representations. One only get some multiple of this relation. But in general, by observing congruences between the forms, between the vectors in our finite dimensional vector space, we can get congruences between eigenvalues of different modular forms. Back to the case, rank 8 is 353. We can find another eigenform with depth 1, such that we have this congruence modulo some prime above 397. As I told you before, this means that the eigenvalues are congruent for all p and k, which gives us the following congruence between the eigenvalues of these two forms. One is a classical modular form, and the other, the Ziegler modular form that we observed earlier. Why 397, you ask? So here's a heuristic explanation. So if one looks at the norm of these values, you can see that the numerator is divisible by 397. Using the functional equation, it seems that it divides the value at 6. And there are some conjecture congruences proposed by Mizumoto and Kurokawa that predict exactly that. So when there's some prime dividing this L value, we expect some congruence between eigenvalues of the Ziegler modular form and the classical modular form. And of course, ours is slightly different because this one corresponds to there are two L functions that you can associate with Ziegler modular form. So this corresponds to the spinor one, and we correspond to the standard representation. So this allows us to conjecture actually new family of congruences. But I think that's the end of my talk, so I'll just say a few words about the algorithmic aspects. The main workhorse is computing these Hecke operators. It's polynomial in P, but with high exponent, which for the L function is roughly n squared. Since there's no more time, I'll not say much about all the improvements and time memory trade-offs. If you care about these things, come ask me afterwards. I'll just show you that all this code is available, and with a few lines of code, you can get your L function on your laptop. And thank you very much.